So now that we already know about what is a heap, min heap, max heap, how to create a heap and how to delete elements from a heap, let's see another way to create a heap. The method that we have seen earlier is the general method to create a heap. And what was the time complexity? It was big O of n log n. I hope everybody of you remember. Now let's see another method to create a heap, which is known as Heapify. So I'll take the same list of elements that we have taken earlier to create the heap using the general method, and I'll show you how Heapify works to create the same heap, but now the approach is a bit different. So Heapify says to create the heap without considering the main condition and then try to put up the condition, check the condition. If it satisfies, then we do not do anything. If it doesn't, then we do the adjustments. So see how this works. When we looked into the earlier method of creation of a heap, what happened? As soon as we were putting the elements into the heap, we were checking for the heap condition. Now what Heapify says, that without checking the condition, we should first create a, I would say, complete binary tree. See, like this. Okay. Now see, I am simply putting up the elements into the complete binary tree. I am not checking whether it is satisfying the heap properties or not. Okay. Then what does Heapify say? It says that pick up the bottommost element. So if we had made an array of this, how would my array be? The array would have been like this now. Okay. Like this. Clear? Now Heapify says that after you have created the complete binary tree, you are going to pick up the bottommost element, which is in this case is 72. So I simply check this element, and for me now rest the whole of the complete binary tree, this part, it is invisible to me. Okay, it is invisible to me. I just have the node 72 with me, and when I have the only node 72 with me, which is this, is it a heap? Say for example, I am creating a max heap. Yes, a single node is always a heap. Then it says, see now 72 is checked. So then it says that check for the next element. So the next element here is 94. So now what is happening basically, I am looking at only two elements like this and 94, which is child of some other node. I don't know which node is here. The rest of the tree is invisible to me. So this 94 also basically acts as a single node because it does not have to check for any heap properties with its cousin. Neither with cousin nor with sibling. The only property check we have to do it is with the parent node. Correct? So we have nothing to check here. It is already a heap. This is also heap. This is also heap. Now next, we pick up the next element, which is 7, like this. So it is like this. Now I can see only this much tree. The tree that you are seeing with the red color, only that is visible to me. So again there is no question of property check between these or these. This is not required. Then I go for this. So somehow there is some 69 here. This is visible to me. But does it have to check any property with 72, 94 or 7? No. So I will say this is also heap. Similarly, I check for 58. This also satisfies heap condition, nothing to violate. Then I check for this particular node. Now for this node, there is a child which is visible to me. Okay, the child of this node, node 8, is visible to me. So here what I do, I can check the heap property. And since I am creating a max heap, I would want to do a swap here. And after I perform the swap, 72 goes here and 8 comes here. Okay. So now only this much tree is visible to me. Now as per this, see now it looks like this. So as per this, does this satisfy max heap property? Yes, it is satisfying. 72 is the parent node, 8 is the child node. It is satisfying max heap property. Next I check for this particular element. So now here 2 is again visible to me. Okay. And I also know its children nodes. So I can clearly see that the max heap property is violated in this part. So I would want to do a swap between these two elements. So this will become 94 and this becomes 2. So here also I will just change it. So here it is 94 and here it is 2. Correct? Now the part of the tree which is visible to us, does this follow the max heap property? Yes. This is max heap, this is also max heap. Next we check for this particular node. So now after this there was 58. So now I have this node also. So for 49, both its children are already visible to me. And what we can see that this violates the max heap property. So we would want to perform a swap here. As soon as we perform the swap, this becomes 69, this becomes 49. This will become 69 to make this 49. Okay. Next I look at this node. So when I look at this node, see 72 is also here. So now this part of the tree is also visible to me. I know about the children of this particular node. So it is clearly visible that it violates the max heap property. So we would want a swap here. As soon as we want a swap here, we perform the swap. Then what happens? 21 comes here to put 94 at this place. Now see, you have changed some values here. So you would always want to look down at the leaf value also. You should always perform a check whether it needs a swap or not. Now after all the nodes we have traversed, it's all now rest of the whole of the tree is visible to me except the root node. So let's look at this. When we look at this, we find that it violates the max heap property. So we would want to replace it with the higher valued child. So we'll replace it with 94. So 35 will come here, 94 goes there. But now see carefully what will happen. Now as soon as you replace this, means perform a swap, what happens is you can check that the child of 35, which is 72, is greater than the value of the 35 node. So we'll again perform a swap. See, this I was talking about, that it's not fixed that always you would only a single swap would do the work. Instead, there might be instances where the swap might propagate down till the leaf. Okay. So see now what happens. We have got our max heap. So we have got our max heap. But now you must have observed that the adjustments took place from a bottom to up fashion, in a bottom to up fashion, bottom to top fashion. And also see, for all the leaf nodes. So if you remember the property of complete binary tree or of any binary tree, what will happen? See, number of leaf nodes will always be equal to number of internal nodes plus 1. Okay. So if number of internal nodes is 5, then number of leaf nodes will be 6. Okay. So this constitutes nearly equal, in fact more than the equal number of nodes. So if you carefully look at Heapify, you have to perform no adjustments for the leaf nodes. So in Heapify, no adjustments are needed for the leaf nodes. Means for nearly half of the tree, for nearly n by 2, if there are total n number of nodes, then for nearly n by 2 number of nodes, no adjustment is required if we follow Heapify method. Then for the other nodes, since they are closer to the leaf nodes, we nearly perform one swap. At some places, like we saw here, 2 swaps were required, but mostly you can see that one swap is enough to ensure the max heap property. Only in the case of root, you may see that log n, that is equal to the height of the tree, number of adjustments might be required. So can you understand that the time complexity, the time required to create a max heap using Heapify will be much less than the general method. So the general method took a time of n log n, because for every element, if there are n elements, then for every node we had to do log n comparisons, log n adjustments. But in Heapify, it gets reduced and it becomes big O of n. Okay. So in maximum, we are going to do n number of adjustments. So from this, we can conclude that the Heapify method is a better method to create or construct a heap from a given list of elements. Thank you.